and we can go ahead and get started since it is just about time for class to start anyway.
Okay, just some real quick heads up. I'm not very good at math. You're gonna have to refresh my brain a little bit.
Well,
Hi, Jen.
Morning.
Good morning. All right, so I see everyone's sort of at home. That's good.
Yep.
And you are?
My name is Jennifer Black.
Okay. And I'm Mike Burke.
Nice to meet you.
Nice to meet you. We haven't had a class together, so in fact, I haven't had any of the people in this class in any of my classes before. So
Oh, wow.
it'll be a great experience for all of us. Harley, don't worry about thinking you're not very good at math. You're actually better at it than you think.
Okay, I'll take your advice.
Yes. Excuse me. And we encourage you to, if you're having any trouble at all, contact Laura or me for tutoring. We're both available.
Okay.
Laura is very good at this stuff.
Okay.
So, and she's very helpful. So she's ready and willing. You just have to contact her by email and set up an appointment.
Okay, I can do that.
Okay.
Okay, thank you.
You're welcome. And Jennifer, you tell me about your experience with math.
Well, I graduated high school in 1991, and we did not require hardly any math for graduation back then. So I think in 10th grade, I had some pre-algebra and kind of skated my way through an algebra class my junior year, and that's about it. But I have a lot of working experience as a restaurant manager in casinos. So I have that working experience with a lot of math, doing like pricing for menus and spreadsheets for the end of the month to see what our numbers look like. So I think I have a lot more working experience than education in it.
And really the experience, the only way you can learn math is to do it.
Mm-hmm.
Okay, yeah, that makes sense.
So that experience will be invaluable for you because you were doing algebra.
Yep.
Whether it looked like it or not. People get scared of algebra. So you'll find through the time here, I'll try to lighten things up. I have a large portfolio of cartoons and jokes about math.
I like it.
And I find that if I can get people to see the humor, and a lot of it is that it makes things a lot easier. Also, I just like jokes. I have to. So,
Well, this is going to be good.
Daughter hates my sense of humor sometimes because I just won't. I let it out, but that's all right.
This is going to be a fun class.
It will actually be enjoyable. I think. I like to think that we can make this not only enjoyable but useful. So we'll be working on doing that throughout this course. The structure, I'm going to let you know there's a lot of noise going on in my house. A week ago today, I walked down to my basement and found a flood.
Ooh. Wow.
And so we've been drying the house out, cleaning it out. Hello, Angela. I'm Mike.
Hi.
Hi, Mike. Hi, Harley. Hi, Jen.
Good morning.
I missed you guys.
I missed you too.
Yeah, there's nothing quite like the open classroom environment for cementing relationships. But we found several inches of water in parts of the basement, and it turns out that we had two problems. The first problem was that for some unknown period of time, our main water line had been leaking and pumping water around the periphery of the basement drain structures.
Oh my Lord.
And then the sump pump failed.
Oh.
So water was pouring in through the sump pit. The guys from Service Master pulled 2,100 gallons out of our basement.
Oh,
Wow.
my
Is the volume of a small swimming pool
Oh,
without
my
the benefit.
gosh. Right.
That's crazy.
So they're back here today, and they understand what's going on, and they're doing their work. And they're gonna try and be as quiet. Of course, they're downstairs. I had to move my office up here, upstairs, which is kind of been fun. And we have
Oh, my goodness. I might be having my maintenance people come in here too, actually, while we're on here. My oven door just randomly fell off the front of my oven yesterday.
Oh no.
Good thing it's warm out.
Yeah, it didn't shatter, thank God, but it's just like, hey, so they're gonna come fix that.
Yeah, that's
Right.
always fun.
Right.
It makes it kind of useless.
Yeah, yes. Yeah, I'm like,
Microwave.
I'm scared to use it. Yeah.
Nuking everything, are you?
I have been. Or
Poor girl.
we went out a lot yesterday.
I
Yes.
bet. Well, I hope you've been doing takeout rather than going.
Yes, yeah, exactly. Definitely.
Now, despite yesterday's instructions from our governor that we could begin to loosen things up, we're going to be online all month.
Okay.
Depending on how things go, we may go back to in-room classes next mod, but we are keeping, that's a possibility rather than a firm decision at this point. We'd like to do it that way, but you know, we have lots of talks with Joel and Katie about these things, and we'd rather be safe than sorry.
Absolutely.
Yeah.
So we will continue for the time with this online classes.
I think
So
that's smart.
what
Yeah, I do
I am doing is I'm recording the class. Anna's here.
Hi, Anastasia.
Hi, Anna.
Sorry, I had to wait for my computer to load.
Mhm. They're
Yeah,
slow
things happen, but
lately.
that's okay. We've just been sort of talking about a few general things first. I am recording the classes. This is not to let people not be here, but because I think I have some people that are going to have a hard time. Also, the purpose of me recording the classes is if you want to go back and review things, you can. I'll be sending you the link to the YouTube version, and you can go through and fast forward to whatever part you'd like to review.
Perfect.
As in the one of the announcements I sent out over the weekend, if you need tutoring, Laura's available. I'm available. Make an appointment. We will be both very happy to help, because all of you need this class to graduate, and we'd like to see you get through it with the least possible pain while you're at it. Now, let me just tell you my take on math. My education, my formal degrees are in chemistry, but I've also taken enough math for a degree in math as well. So I know a lot about math, and algebra for me is a second language. So, I mean, it's easy. Algebra does have its own terminology, its own language. We'll go over a lot of that. It's mostly straightforward, but occasionally there are some things that are just unusual. So we'll be working through that. We'll get started on that. The structure will be, we'll have some lecture time. We'll take a break and let you work on assignments and discussions for a little while. Come back and have some more lecture time, because I can't imagine what I'd feel like if I just talked for 3¼ hours. You don't want to listen to me for that long anyway. So we'll break it up with that, and I will always be here. We'll always be online for the full 3¼ hours. I will try and remember to turn off recording during breaks so that we don't have a lot of dead time in the recordings. But we should be able to get through all the material we have. We will have at least one in-class activity every week, and it's not going to be posted, so you have to be in the class to do it. So and the fact that you're here, I've got the 4 of you now. There are actually supposed to be 7 of you, and I hope that works out for all of us. Anyway, usual class structure: discussions, assignments, assessments. The assignment this week has a worksheet. We will spend some time on looking at that assignment on Wednesday. I'd like to get some other things out of the way today as we go through this class. So, questions?
Not yet.
What will our discussion look like for math?
Let's go take a look at it.
Okay.
Okay. Okay, can everyone see this?
I can.
Okay.
Yes.
So the discussion, that's actually a very, very good question, Harley,
Okay.
because it's kind of hard to see what you discuss when you're doing math. But in reality, the discussion is related to how you're going to apply it and what you need to know.
Okay.
If you look at this prompt, we have a student who's taking a degree and then sees that she has to take algebra and begin second guessing that degree, okay? So you're going to be talking about the importance of understanding the foundation for algebra for your career, and then look at skills that you might need to make use of that math. And if you look, I've already made my first post. You can read that. I'll let you read that on your own. But there's the background material, just gives you some material and some references you can go to and take a look at as part of your research for the discussion. And in fact, I thought later this morning we'd take some time and you'd get started on that.
Okay.
So really, it's not about discussing the actual maths per se. It's about looking at the application and how
Okay.
it's going to affect your career.
Okay.
Does that make sense?
Yeah, absolutely.
Okay, so let's back up. One thing, since I have not had any of you in classes before, I would like you to go ahead and post on the introduce yourself. Excuse me.
So on my shoot, what am I trying to say here? My shell is like, it just says in class assignment.
Right.
Is that what we want to click on?
No.
Okay.
The in-class assignment will be something that I specifically bring in. I'm looking at outside resources for some kind of fun things to do.
Okay.
And ways to illustrate the basic principles of algebra that we're learning.
Okay.
So that'll be completely different. Every single in-class assignment reads the same thing. We'll be doing something related to this week's work.
Okay.
So I haven't quite decided what all those are going to be yet. But we will be doing that. And we'll be doing that generally on Wednesdays, because I'd like to get the basic principles of the week out of the way on Monday. And then on Wednesday, we'll be doing the the other.
Okay.
Okay. Okay. Does that help?
Yeah, that does.
As I said, since I have not had any of you in class before, I'd like you to do this introduction. The question about when about learning something you thought was pointless, I'm not so certain I care so much about that as what it is you think you might be doing with algebra in your career. So I'd like to know what your majors are, and I'd like to know your background. Okay, because everybody here is different. Jennifer was talking about working in the what we call the hospitality industry, to some extent, restaurants and casinos and things, and what she had to do there. Everybody has a different background and a different reason for being here. So I'd like to know more about that. Okay, about each of you. So I can understand where you are and maybe understand some of your concerns. All right.
Okay.
Okay. So we've talked about the discussion and the introduce yourself. Let's take a look at the learning objectives for the week. And what I'd like to do is, just let me check something real quickly here. All right. What I'd like to do is look at these learning objectives and play a short video. So our learning objectives this week, we're going to talk about something called sets. Now, sets sounds like some weird concept, and there is a whole field of set theory in theoretical algebra, which is not what we're going into. Sets are really groups of objects called members of the set that have some consistent property relationship. A set can be the set of integers, meaning whole numbers, what we call the counting numbers. They can be the set of irrational numbers. These are numbers that we'll define later, but they have a common property and a common use. So there's also something called a null set, which is nothing is in it. And that's mathematically, it's more important than it will be in this class, but it is just one of the components. Okay. We're going to look at exponents. You've all seen exponents. You've seen x squared and cubed and so forth, but we're going to look at those. We're going to look at algebraic expressions and the purpose of those. That's what you're talking about in the discussion. And this thing called PEMDAS. PEMDAS is a structured method for solving equations that can give consistent results and tells you how to properly solve. And we'll go through that in a lot more detail today. Okay, so let's take a look first at this little video. I'll make it big enough to see.
Jessica landed her dream job, a position in an accounting firm, and she couldn't be more excited. After all of her schooling and midnight study sessions, her work is paying off. As she begins her work, she is amazed by all the concepts pertaining to algebra that she needs to pull from in order to perform her various roles, including tax returns, summarizing important financial documents for clients, and much more. She quickly realizes she needs to use information relating to number sets, exponents, algebraic expressions, and, of course, how to solve those algebraic expressions using PEMDAS. She knows that exponents make multiplication much simpler and that PIMDAS helps her correctly solve long equations. All of those things are important in accounting. Jessica knows her college algebra course has prepared her for this exciting season of life, and she is excited to get started and see where her new career will take her.
Okay, so that sort of brings us as a quick explanation of where we're going to go this week. Don't get bothered by that huge page of equations. We won't be dealing with anything quite that complicated. But we will deal with things on a regular basis that will have a number of different, what we call terms in an algebraic expression. And so the purpose of this week is to sort of set things up to do a lot more work the next few weeks. Okay? So let's go back. All right. One thing I will remind you is that if we look at the announcements here, we've got the announcement of MAT updates. You've probably seen this. That's tonight at 6 p.m. If you can possibly be on. There will be a number of things going on during the MAD. We have prize drawings, perfect attendance. Those that have perfect attendance will go into this drawing where we have possibly a PlayStation 4 Slim as a prize. The Success Center drawing is something you get a ticket for the television or the Amazon $50 gift cards every time you are in the Success Center, either with Laura over Zoom or any other way. Okay. So when you go and go in there and talk with Laura, she should give you a ticket for that'll go into for the drawing of those. So that's not the only reason you should use Laura, but it's a little bit of an incentive to take advantage of her expertise.
She's really good with it too.
Yeah, she is. She has helped a number of my students because I also teach the medical math class. So she's been very helpful with my students there. And I've taught this algebra class in one form or another for several years here at the school. I was saying earlier that my background is in chemistry. That is my formal degrees. But I have enough math to actually have a degree in math as well. You can't do hard science without doing a lot of mathematics. So I've used math in one form or another in virtually every job I've ever had. And I've had a number of them in a fairly long industrial career. So, so math is, for me, almost second nature. If I get to going too fast, and it is something that might happen because to me, it's so easy, stop me.
Okay.
You know, I run a very informal class. So if I'm going too fast or if you have a question, stop me right there.
Okay.
Especially if you have a question, if something is not clear, you know, when you stop me, it'll be at the top of my mind and I can go back and perhaps be a little clearer in the explanation.
Okay.
But if you wait until later, both of us have sort of gotten out of that mode of thinking and I may not be able to get back into it real fast.
Okay.
So, but please do, you can do it several ways. I don't know if you have reaction button or not that allows you to do a thumbs up or put up a hand on your little thumbnail. But you can also just raise your hand or say something. So be aware that I'm not terribly formal about these things, and I don't care if I get interrupted. So let's see. You have an assessment each week. The assessments are structured so that you can do them multiple times. My attitude about assessments is that they should be a chance to learn, because you learn from doing something wrong the first time. There is no shame in getting a problem wrong. The shame is not learning what you did wrong and then correcting that. So you get a chance to do these assessments several times. There's no reason that all of you shouldn't have a perfect grade on the assessments at the end of the day. So that is part of my feeling about those, and that's going to hold all through the class. Okay. All right. So let's go ahead and get started. There's a couple of things that I would like to start off with. We have this set of instructional resources here that we can look at. And what I'd like to do is get started on discussing numerical sets. Remember, I told you that sets were just a group of things. And a numerical set is just a collection of numbers of some sort. The objects, the members of the set, we call elements as well. The term is the term element or member means the same thing. We've got even numbers. We've got odd numbers, meaning even numbers all by definition can be divided by 2. Odd numbers cannot. We have prime numbers. Prime numbers are numbers that can only be divided by themselves and 1. And by the way, if you divide any number by 1, it's the number. So 3 divided by 1 is 3. 900 million divided by 1 is 900 million. So that's another principle to remember. So prime numbers are numbers that can only be divided by themselves and 1. Prime number theory is an interesting topic. We will not go into it, but it's important to understand that principle when we start doing solving equations. So we can define a set any way. One of the things I have here, positive multiples of 3 that are less than 10. So that's 3, 6, and 9. That's a set. Common characteristic is that they're divisible, evenly divisible by 3, and they're less than 10. So that's a defined characteristic. So we can define our sets any way we like. The ones that we use throughout algebra are, as I said, the null set, the empty set, which is, we give as a symbol. Sets are often put into these brackets, or braces rather, not brackets. And we consist, and an empty set can be represented by brackets enclosing nothing, or an O with a slash through it. Counting numbers. starts with a number and continue in sequential order. 1, 2, 3, 4, 5, 19, 20, 21, 40, 41, 42, etc. That any of those can be a set. We just define the what we call the limits of the set. In other words, the lowest and highest possible value. Whole numbers, the only difference is here is that between that and the counting numbers is whole numbers include 0. Okay. Integers integers are numbers, whole numbers, but the integer set includes the negative components as well. So here we have -3, -2, -1, etc. So the integers are a set that go as far negative and as far positive as we want. Rational numbers are numbers that can be expressed as one integer over another. In other words, a fraction. 1/3, 1/4, 1/5. These are rational numbers. Irrational numbers are numbers like the square root of 2. A square root is merely a number that multiplied by itself will give the number under this thing called a radical. So the square root of 4 is 2. 2 times 2. The square root of 25 is 5. 5 times 5. So square root means something that multiplied by itself will give whatever the base number is. Some of these things do not have, if you divide if you try to figure out what is that value doesn't end in a nice even number. The square root of 2 is a number that goes on essentially forever without repeating. So the square root of 2 is most often rounded off to 1.41, simply because we can't have a number that goes on to, to 17 million digits and work with it. Okay? So we round these off, and then when we go back to multiply 1.41 times 1.41, we don't get quite 2. We get something slightly less. So, this is a look at what these are. Another famous irrational number is called pi. Pi is the ratio of the circumference, in other words, the length around of a circle, to the diameter, a line that goes directly across through the middle of a circle. That ratio is called pi, and it is 3.1415. It goes on forever, and it never repeats. That's also an irrational number. There are an amazing number of irrational numbers. That's not going to be a terribly important part of this class, but it is something to understand that we have rational numbers that we can express as fractions, and irrationals which are non-repeating and non-terminating. What's a non-repeating? Well, the square root of 2, 1.414, blah, 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 goes on for a long time, but there's no pattern. That's what we mean when we say non-repeating. It also never ends. An example of a rational number that ends is going to be 1/5. If you divide 5 into 1, you get 0.2. And that's it. That's as far as you have to go. If you divide 3 into 1, you get 0.333. Goes on forever, but that's a repeating decimal. That's a repeating decimal sequence. 1/9 repeats as as 0.45454545 again forever. So that is a rational number because it repeats. The difference here with the irrationals is there's no repeat and it never ends. They have calculated the value of pi out to something like a couple of 100 million decimal places, and it never repeats a pattern. So that's why we call them irrational. It means that we can't express them as fractions. Can we approximate them? Yes. One common approximation for pi is 22/7, but that's only an approximation. The only thing that we can say is that we can get close but not exact. Okay, so that's the difference there. So what I'd like to do is go ahead and play this video right now. Unless there are questions, please ask any questions.
Not yet.
Okay. So if we want to do this, we'll just go ahead and do this video.
Welcome to Discrete Mathematics. Let's start with set theory, which is a very fundamental notion in the entirety of mathematics. So what is a set? A set is a collection of objects called elements. And this is very vague because we can have a set about anything we want. And usually we talk about sets by drawing these little circles. So for instance, if I want a set of, let's say, the numbers 1, 2, and 3, I can draw a circle and I can put the numbers 1, 2, and 3 in there, and that is a set containing the numbers 1, 2, and 3. And we can write this formally in curly braces and writing all of the elements inside. So in this case, our set contains 1, 2, and 3, and we can give this a label and maybe call this A. So these are all different ways of representing the same thing. A is the set 1, 2, and 3, which looks like a circle containing elements 1, 2, and 3. Of course, this is just visual, and this notation in curly braces is called a list notation because you're listing them all. Now, sets can be finite or they can be infinite. So we can have a set A containing all the numbers between 1 and 9, or we can have the set of positive integers that go from 1 all the way up to infinity. And in this case, this is an infinite set. So these ... dots mean that there's an implied pattern that just goes on forever. So here, Z plus, if we have 1, 2, 3, 4, and we put ... we mean that it goes 5, 6, 7, 8, 9, 10, so on and so forth. So those are really the fundamental notions of sets. Now there's some additional points to these sets, and that is that repeated elements are only listed once. So if we have a set A, B, A, C, B, A, even though A is repeated 3 times, we only write it once. B is repeated twice, we only write it once, and C is repeated once. So this set ABACBA is the same set as ABC, and they would both be drawn as circles with some element A, some element B, and some element C. In other words, we don't care about the amount of numbers of these things in there. We don't care if there's 3 A's, we don't care if there's 2 B's. We just want to know what's inside our circle. There's also no order in a set. And in a diagram, this is easy to see because there's no order in a circular diagram. But essentially, the set 3, 2, 1 is the same thing as the set 1, 2, 3. And that's also the same thing as the set 2, 1, 3, so on and so forth. There's no order to these sets. So those are 2 pretty important parts. Usually on an exam, you might be given a set that has repeated elements, and they might ask you, how big is this set? How many things are in it? And if you're not sure about repeated elements, then you might get the wrong answer. There's a few common sets that we should talk about. One of them is the natural numbers. The first time I made this video, some controversy. And there's still some controversy. But there's 2 ways to do the natural numbers. One of them is to start with 0, do 1, 2, 3, all the way up forever and ever. Another group of mathematicians starts the natural numbers with 1, 2, 3, so on and so forth. I'm going to refer to the natural numbers starting with 1 as the positive integers. And when I talk about natural numbers anywhere else, I will usually mean including 0, but I may be more specific about it. So I will specify whether it includes 0 or not. But typically with 1, 2, 3, so on and so forth, I'll use Z plus. The integers are a set of numbers which are either positive or negative, and they're whole numbers. So all the way from negative infinity, -2, -1, 0, 1, 2, all the way to positive infinity. So that is Z. That's a very important notion, which we use a lot in discrete math. And then rational numbers. Well, these are kind of hard to list. So I'm going to cheat a little bit for now, and I'm going to say, well, we have like 1/1, 1/2, 1/3, 2/3, so on and so forth. And in a few slides, we'll figure out a better way to write this. So of course, rational numbers are any numbers you can write as a fraction. So elements and cardinality. Now we know what sets are. Now we know some additional pointers about sets. We know some common sets, but we want to be able to talk about the things in those sets and how big those sets are. So I have C, and I have a set containing yellow, blue, and red. So these are the primary colors. In fact, sets don't have to be all mathematics. They can be words too and have meaning in the real world. So I want to say something like yellow is an element of C. And this means that yellow is inside of our set C. Now, how do we write this? Well, we have an element yellow, and we want to say it's part of a set C. So in order to write this in notation, we use this epsilon. So yellow is in the set C. What about saying green is not in the set C? So I want to say green is not in here. In fact, we don't see it in the set C. So what do we do to say green is not in C? Well, we use the set membership symbol, and we just put a line through it to mean green is not in our set C. How do we talk about the size of this? How do we say the size of C is 3, which means the amount of things in C is 3. There are 3 different elements in C. Well, we just draw these absolute value bars around it. So we say that the absolute value, or the size of C, is equal to 3. And that says that the cardinality of C is 3. So now we can talk about whether things are inner sets and how many things are inner sets. Now there's one particularly interesting set that contains nothing in it. This is called the empty set, and this is written with this symbol. And if I wanted to write it in the set notation with curly braces, it would look like this. It has a left curly brace, a right curly brace, and then there's nothing inside of it because it's empty. So what's the size of this set? Well, there's nothing in it. So the size of it is 0. And there's only one set that has a size of 0, and that is the empty set. So here's a question. And I'm throwing this right at you right away because this trips people up all the time. What is the size of the set containing the empty set? So I'm asking, if I have a set containing the empty set, what's the size of that set? Well, this empty set is an element of the larger set. So the size of the set containing the empty set is 1, because this set itself, this big set, has one element. It has an empty set as an element. So sets can have sets as elements. We'll see another example later, but typically I like to look where the commas are. So if there's like a big set, then a comma, then another big set, and that's all it's in the set, then there'd be 2 elements. In this case, we have these empty braces, but there's something inside of it. So therefore, there's an element in that set. This is different, of course, than the size of the set containing nothing. This would be 0. So we can see the contrast between these 2 sets. This is the empty set on the right, while this is a set containing the empty set on the left. The left one has a size of 1, the right one has a size of 0, and we can see the differences visually. Okay, so that's the empty set. There'll be more questions about the empty set when we get to the subset video, so more tricky stuff will happen there. The next thing we should talk about is set builder notation. So before I introduced the rational numbers and I said, oh, it's 1 over 1, 1 over 2, 1 over 3, 2 over 3, so on and so forth, there's got to be a better way of representing this entire set. And this is set builder notation, or we can call it maybe predicate notation, where we define elements as variables. So for instance, I can say this is the set containing elements that are of the form m over n, such that, so this straight bar means such that, and now I'm going to give a rule. So the left is like the form that it takes, and on the right side, we're going to give it a rule. We're going to say that m and n have to be integers, and also n has to not be 0, so that way we're not dividing by 0. And this expresses the entire set of rational numbers. I'm saying, look, take any two integers, m and n, we can put m on top of n, and as long as n isn't 0, it's going to be in that set. So I'll do another example with even integers. So we can write all the way to negative infinity, negative 4, negative 2, 0, 2, and 4, so on and so forth to infinity. Or we could do this in set builder notation. So we could say this is the set of 2n such that n is an integer. So what this means is we take an integer n, so let's say we take 1, then in our set we add 2 times that integer, so 2 times 1, so we add 2. Let's say we take 2, then we take 2 times 2 and put in our set 4. Let's say we take negative 1, then we take negative 1 times 2, and then we get negative 2 in our set as well. And this just goes on forever. So for every n that is an integer, we add 2n to our set. And that gives us the set of even integers. So here's a more linguistic example. So something we can apply in the real world to see how this notation works. I have a desk. And on this desk, I have a drink, I have a laptop, and I have a microphone. And there's some other things on my desk that I could list, but let's just say my desk only has these 3 things. Now, this is one way I can talk about things. I can say I got this drink, this laptop, this microphone on my desk. Or I could write this in set builder notation if I might have a lot more things, or maybe I want to be vague, or maybe I'm not entirely sure what's on my desk, but I know there's things on my desk. So I could rewrite this as the set of x. So this is a variable x. And what's the condition for x? X is on my desk. Yeah, so this is kind of cheating, right? But they're the same sets. So the first one, I'm listing all these items individually. The second one, I'm saying, look, it's the set of variables x, and whatever x is, it just happens to be on my desk. So everything that's on my desk, it's just going to shove it in as x, and it's going to build a set with it. So that's the set builder notation. And of course, mathematically, we do this very formally with, of course, numbers and formulas and notation. Well, of course, if you do a linguistics example with words, it's much more wordy, it's much more flexible, much more floaty, but they both convey the same meaning. So if you didn't quite understand the mathematics example, then hopefully you'll be able to translate this desk example back into the mathematics after, while maybe understanding this at a more fundamental level. So here I have some exercises. And these all refer to the first 2 refer to the set D, and the third one is completely different. Try them yourself, and if not, well, I'll give you the answers now. So list the elements of D. D is the set of x in positive integers such that x is less than 6. So I'm going to take all x less than 6 and add them to the set if it's a positive integer. So this means that I can have 1, because 1 is a positive integer and is less than 6. Let's do this in a different color. 2, 3, 4, and 5. Can I add 6? I can't add 6 because x is not less than 6. Can I add 0? Well, I can't add 0 because I specifically want the x's that are in positive integers, and 0 is not a positive integer. Okay, what's the cardinality of D then? Well, this is easier because I've already written out all the elements in my set. So I see there's 5 things there. So I can say the cardinality of D is equal to 5 because it contains the numbers 1, 2, 3, 4, and 5. But here's another question, and this is what I alluded to before. What is the cardinality of the set containing the empty set and the set AB? Okay, so how many elements are in the set? And when we look at sets, it's kind of like looking into a box and saying, well, what can I see? I see an empty set and I see another set. So really what I see inside this box, if I were to draw this out, is a box containing nothing and a box containing A and B. So the stuff inside of these boxes, essentially with a cardinality question, these things are invisible. We can't see what's going on. So the question is, how many things do we see inside that set? What is the size? How many elements are in that set, that big box? And the answer to this is 2. And this is why I said look at the commas here. So we have an empty set, which is the first thing. Then we have a comma. Then we have this other entire set. So there's 2 things we can see. Now, how does this differ from, let's say, if we have a set containing the empty set, the set containing A, and then the set containing B? Well, this is different, of course. So in this example, if I were to draw this, we have a box containing nothing in it. We have a box with A in it. And then we have another box with B in it. So how many elements do we see? Well, we can't see inside these boxes. But if we just open our box and take a look, we'll see 3 other boxes. So in other words, the size of this would be 3. One more example. Let's say we took away one of these. So now I have something that looks like this. I have the empty set, I have the element A, and I have a set containing B. Once again, there are 3 elements that we can see. We can see this box containing something, we can see the element A, and then we can see this box containing something else, which happens to be B. So once again, this cardinality is equal to 3. So that is it for the Introduction to Set Theory video. If you have any questions, please leave them in the comments below, and I will do my best to answer them.
Okay, so let's discuss that. There's a couple of things I would like to explain. First off, this is more information than is absolutely necessary to understand the idea of sets. But the idea here is that sets can be groups of anything. They can be groups of flowers in your garden. That can be the set of flowers in your garden. And depending on how many flowers, you have that many elements in the set. Doesn't matter if you've got 30 tulips and 80 daffodils. There are 2 elements in the set, right? So the issue of set builder notation is something we may run into later in the class. So I wanted you to see that entire video. Couple of things, terminology. Mathematics uses a lot of symbols. One of the things we'll talk about is what those symbols are in math and what they mean. So we'll do some of those as well, maybe later on today. But you saw the little carrot on its side, the little thing that was like half an arrowhead pointing to the left. That is a symbol that means less than. If it pointed to the right, it would mean more than. And in the case of that particular example on one of those slides, if it had been more than the value of more than 6, it would exclude 6 because it would have to start at 7 if you're talking about the integers greater than 6. And then it would go on to infinity. So the number of elements in that set would be infinite. Does everyone understand the concept of infinite?
Yes.
Yes.
Okay. Yeah, because it really doesn't, you know, we're not talking Buzz Lightyear here. We're talking about math. And in math, infinite means uncountable. Okay. It means no end. And sort of like thinking, where's the end of the universe? It's pretty far out. But we know there's an edge. At least we think there's an edge. But with math, anybody that tells you, well, the biggest number is X, somebody just says, well, add 1. Then you've got a bigger number. So there is no limit. And it can go in both directions. It can be infinitely small, it can be infinitely large. So the issue is the thing to remember is that part of that notation for describing a set is to use the triple dot that says it just goes on forever. That means out to infinity. We do have the infinity symbol, which looks like the letter or the number 8 laying on its side. But we don't like to use that too often because it doesn't convey the proper information in many cases. So also we will talk about some of the arithmetic rules, remind you of some of the arithmetic rules for multiplication and division as we go along too. And for addition and subtraction. So the language that he's using is pretty standard, but it does have some things that are unusual. Okay, I encourage you as part of your study to look at these additional resources. I'm not going to play all of these things. These obviously are written resources. The introduction to sets describes what we just saw in words and sets and types of sets. We're talking about mathematical sets here, numerical sets in an algebra class. But the important thing to remember is that a set can be a set of sets, as he pointed out. And then the individual elements are each set. And you can have a mix. You can have a mix of sets and objects. He talked about the null set plus A plus the set containing B. So there's A in that case would be an object. Okay, so questions?
Sure.
Not so far? Okay. So we will be talking a fair bit about concepts. So one of the reasons that that I wanted to introduce you to the idea of irrational numbers as well as rational numbers is because rational numbers, we will be working with a lot of them. Rational numbers are merely fractions. And fractions can have exact values, or they can have values that can only ultimately be approximated. 1/3 is a good one. 0.33, et cetera, forever can only be approximated in calculations. But what we do is we work with these things as fractions in order to limit the inherent error that comes from any approximation. Does that make sense?
Mm-hmm.
Okay. All right. Let's take a short break at this point. Maybe 10, 15 minutes. for people to get coffee or use the facilities or whatever else you need to do. And I will stop the recording temporarily at this point. Somebody remind me when we come back to start it up again. I typically forget, which is not useful. So I'm going to pause the recording. Okay, well, I'm back. Started the recording again.
I'm gonna mute myself because I'm yelling at this dog. So,
I think I'm gonna have to too. One of my cats is acting weird. He
what
keeps
is going on? He's
around.
going wild.
Yeah, mine was too. I opened up the window and he started acting like a weirdo.
Got this puppy next door won't stop. So muting me.
That's all right.
I'm
Just
keeping
remember to
myself
unmute
muted
when
just
you
in
have a
case.
question.
Yeah.
Okay, for those that joined a little later, there's a lot of noise in the background because we had a basement flood last week and we're having a lot of work done in the house today. So you'll hear some noise. The workmen are real good about being as quiet as they can, but it's kind of hard to disguise the sound of a hammer.
Right.
Yeah.
So, and my wife will walk through periodically. I don't know if you're seeing her, but she's working away on it as well. So,
Right.
never enough fun.
Always something, isn't it?
Isn't that the truth? Okay, so we talked about basic
Say
about
hi.
sets. So what I'd look at here is basically to go back and do. I'll suggest that later on this morning you go back and look at this algebra basics video here. It's kind of fun, and he'll give you a little bit of more background. But I'd like to move on at the moment to something slightly different. Let me bring something up here. All right. All right. Okay, so I have a blank screen here. I thought I'd just use some notation and some things that we can note. I will, when I'm done with this, I will actually post it in as a page that you can refer to. Number one, in algebra, general purpose of algebra is to solve problems, and is to determine a value of something that you don't know the value of based on items that you do have a value for. Okay, so one is the concept of the unknown. I'm going to make this both bold and larger. Unknown is what we also call a variable. If I could spell. It's a variable whose value is to be determined. Okay? And it can be represented in a lot of ways, usually by X or a small x. But we want to be careful about how we use X as our unknown, because X is also the symbol for multiplication. Okay, so we will try and pick different symbols for the unknown variable in this class. And it can be anything we want. X just happens to be a standard that we use in algebra. But we can have, it can be A, it can be M, it can be anything we want it to be. And commonly, we actually use Y as a variable as well, simply because X and Y are next to each other. But A and B are used. We also have to be careful about the use of some of these terms because they also have other meanings. So what we're going to try and do is here is keep that terminology to a minimum. Okay, so an unknown. So we have a term we call the constant. And this is a term whose value never changes. Okay, so a constant. Generally speaking, this is going to be, for our purposes in this class, a number. Okay. Generally a number, and that number can be any of these numbers. It can be an integer, it can be a fraction, it can be a decimal. Decimal is merely something that has part of its term is less than 1. It can be a rational number, it can be an irrational number. It can also be something we call an imaginary number, but I will get to that later. Okay. So let's talk about a couple of things. We have positive and negative numbers that we can work with. Now, in the real world, negative numbers are a concept. You can't have for instance, a distance that is a negative number. Okay, if it's, whether it be an inch or 10,000 miles, they're understood always to be positive numbers because you just don't have a negative distance. That's something that is a concept that just doesn't make sense. But they can be positive and negative. Okay, we represent them by the positive sign or the dash. Okay, so let's look at concepts here at this point. With these things, so we have we can have in the absence of a sign, meaning positive or negative, assume positive. So negative numbers, any number without a sign is assumed to be positive. Let's go to.
So no matter what, that's always anything in the absence of a sign, it's always going to be assumed positive?
Yes.
Okay.
Unless it is explained, unless you are told that it is a negative number that you're working with, but it's bad form not to put the minus there
Okay.
because it's confusing. And
Okay.
the
Yeah.
the
Absolutely.
last thing we want is confusion. And I'm
Yeah.
talking about, we know what we're thinking when we're doing these things, but other people don't. So in my class, the absence of a negative is a positive.
Okay.
Okay? Morning. So let's move on here. So we have a number of different algebraic and mathematical functions that we use. So I'm going to give you functions. These are actions that we take. Functions are actions taken by our numbers or elements, because we can have these actions can be taken by rather than elements, variables. And I'll get to what that means in a minute. So and if I don't get back to something when I say I'm going to, call me on it, please. Because I sometimes think ahead of myself and get lost. So these actions are things like addition, subtraction, multiplication, division, etc. Let's just. Thanks for getting that out of here.
Yeah, no problem. Thank you, guys.
You're doing us a favor.
We can also have exponent, and what we call roots. These are all things that are done. Okay. So we'll give some examples of these at this point. Addition should be obvious. And that could be 1 plus 2. It can be A plus B if it's variables, or it can be A plus, say, 5, a constant, okay? So that's the addition function. We simply combine them. We all know about addition. We do it all the time. But I just want you to know that in algebra, we see the combination of numbers and variables, okay? Subtraction. It can be, basically 1 minus 2 to give us a negative number, right? Or it can be 3 minus 1. Doesn't matter. It can be A minus B. It can be A minus 4. Any of those. And A here, I use A. It can be any symbol that we want to use for our variable. Okay. We can also we can have these. Now, less commonly, we can express them as minus 2 plus 1. Okay. So that is essentially the reverse notation for a subtraction. You are still taking 2 away from 1. So there's another way of doing that. I will avoid this as well. It may come up in problems that you see. Okay? So just be aware that this is the same thing as subtraction. Subtraction and addition are what we call, or addition rather, whoops, let me back up out of there. Addition is what we call commutative. In other words, it can be reversed and mean the same. For example, 1 plus 2 is the same thing as 2 plus 1. Okay? Subtraction is not commutative. Subtraction, you can't say that 1 minus 2 is the same as 2 minus 1. You can, the only way that you can reverse is to remember to carry, is we have to include this positive sign on the 1 because this is assumed positive in this, right? So if we reverse this, we need to specifically note it. So subtraction is not considered to be commutative. You can't just switch the numbers around. This is important when we get to solving equations. Enter. We have multiplication. We've got 2. And here is where we get into a little bit of trouble. We often use the X for the multiplication symbol, but we have to be careful that we're not mixing X as a function and X as a variable. So when we are using X's, we should, as our variable, we should use the dot. Now this is also 2. Now a lot of times the dot, whoops, the period, we have to be careful with that as well. So we want to use the star symbol. 2 times 1 is the same thing, 2x1 and 2 star 1. Remember, the star is what we use on the calculator keypad to multiply. Okay, so we can have that. We can have A times B, which we prefer in many cases in when we're writing out things as A star B. Okay. And we can also multiply, and we will commonly see another form here. And again, this is a set of assumptions. AB means A times B. Two A is 2 times A. So when you see a notation like this, we assume that this is a multiplication. Does that make sense? So we use a lot of assumptions, and we use a lot of standard practices that require us to make those assumptions. Remember, in the absence of a sign, we're assuming it's positive. In notation for multiplication, we can use the X or the star, but without them, we assume that it's multiplication. If we just have these two together, no space between them, it's always considered to be multiplication. Okay. Now remember here as well that multiplication is also commutative. In other words, 1x2 is the same thing as above. BA is the same thing. It's multiplying A times B. It's exactly the same. However, we always, by convention, when we're multiplying a number times a variable, the number goes to the left of the variable. That's convention. It could go either way. But we generally do it, use the convention that it's the constant first and then the variable. Does that make sense? Okay. So you should never see anyone who does A2. So multiplication is another commutative term. Now we have division. Division can be, is simply dividing one number by another. And we can have 1 divided by 2. So we have the slash symbol we can use. Let me see if I can find I can do an insert here. I can find that symbol real quickly. Yeah, there we go. 1 divided by 2 is another way of putting this. And we can also have A divided by B. We can have 2 divided by A, or A divided by 2 or any other constant. But we can express division in using either of these symbols. Okay. So division is not commutative. 1 over 2 and 2 over 1 are not the same thing. Rules, so let's put down but another couple of rules here, or another couple of things that we need to follow. No, come back. Okay, so in terms of division, where was I going with that? Division is not commutative. Division is usually done by convention. There's no reason that we do this, but we use these terms here, and we try to express. Here is where definitely the order counts. You can see the 2 over A and A over 2 are very different. Okay. So division by 1 of any number or variable by 1 equals the number or variable itself.
So 3 divided by 1 would be 3.
That's correct.
Anything would be itself.
Yes.
Okay.
And another thing, we talked about fractions. Any number or any variable, anything else, any element of any set can be expressed as a fraction simply by putting it over 1. Right? So as 3 is also 3 over 1. That gets useful when we are working with multiplication of things like fractions and division of fractions. Okay. Good question. All right, so let's take a look at now exponents. Exponents are a term that can be expressed in several different ways. We can have 2, and on the keyboard, we use the up caret to indicate if we want to have an exponent of say 3, we can do it that way, or we can do and use the font key to make that a superscript. that notation, okay?
Okay.
Those are exponents. So what an exponent does is it multiplies the base. This number here, the 2 in this case, is called the base. By itself, the number of times that the exponent lists. So this becomes.
So it'd be 6. No, my bad.
So this becomes 2 times 2 times 2. So what we do is we set it up as serial multiplication. Okay. What I call serial multiplication. Our calculators, we can do these easily. 2 times 2 is 4, 2 times 4 is 8. So in this particular example, let's go here. Okay, we've got 2 times 2 times 2 can also be written as 2 space x tape space 2 space x space 2 if we're using that notation, and it equals 8. So we multiply 2 times 2, and then we multiply that product by the 2 again. So another example can be, say, 3 to the 4th power.
Okay.
Which is also, it's a little more cumbersome to do the superscript. So I'm going to stay with the caret notation. Is that all right with everyone?
Yeah, that's fine.
Okay, so this becomes now 3 times 3 times 3 times 3. Okay, which equals 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81.
Holy crazy.
So you can see these things go up. This is what we talk about when we talk about lately about this coronavirus. They're talking about exponential increases. That's because you can see that when you start multiplying these things, we get up to big numbers in a hurry. And the bigger that exponent is, the faster these things grow. Now, let me give you a famous example. One of the 1001 Nights stories is of Sherazade making a bargain with the king that if she puts a small piece of money on the first square of a chessboard and then moves to the next square and doubles it, and the next square after that and doubles it again, etc., that he could that he would pay her that money, right? Well, here we have an incredible number. It is 2 to the 64th power.
Holy moly.
That number is enormous. Let's go to our calculator, and I think we can do the scientific calculator thing here. My computer calculator does not like that one. Okay. So this is kind of a, let's see, what do we got here?
What is it?
Here we go. Now I can do it. Okay, so we have x to the y, right? So if x is 2, and then we put in the y, which is 64, we get that number. Look at that number.
We're not able to see. I don't think we're able to see.
You're not seeing.
Yeah,
Just a second. Let me see if I can bring that. There we go. We got the calculator. Now can you see it?
Yep.
There we go. Look at
Okay, so
that number.
what did I do wrong?
That number. Hundreds, thousands, millions, billions, trillions, quadrillions, quintillions. 18, that's a lot of coins, right?
Yeah.
That's how fast exponential notation can make numbers exceedingly large. And we use these, especially in science, where we get some very, very large and very, very small numbers. Now, we can also, I'm going to leave this up here, we can also have negative exponents. Negative exponents are and I'll write out some of that notation in a moment, but negative exponents can be done as well. So if now we've seen this number, 18 quintillion, which is just a mind-boggling number. If we now put in x, no, let's clear that before I get in trouble. Okay, we've got 2, and then we want to put in minus 64 as x to the y, and we get a number that is gigantic, right? Oh, no, that's wrong. They did the wrong thing to me here. Please excuse me. We'll just get all that cleared out and try that again. 2 x to the y minus 64 equals, they didn't like that. All right. What am I doing wrong now? Okay. 2 x to the y minus 64. Now I got it correct. No, it didn't like that. It doesn't like that number. Anyway, it's a very, very small
put a variable in between
Pardon?
it. You have to put a variable in between it. I know it's very strange for that. The calculators don't normally like it when we have numbers.
Yeah.
Or not numbers, but letters in with numbers.
Okay. So we've got 2, and I want to do x to the y. So it's got that properly figured out.
Until you hit the minus or plus or multiplication or division, it disappears.
It sure did. All right, I've got a better idea. Let's clear all this out. X to the, no. 2 x to the y, and we'll put in minus 64 in parentheses. Nope, it's 0 minus 64. Well, let's see what happens. There we go. This means times 10, this means this is a fraction over 1 over this huge number. So this is scientific notation, e minus 20. This is 10 to the minus 20th. So it's a very small number. There aren't there are very few of those numbers you'll ever work with. So let's get out of here and go back to sharing. Oops. Go back to sharing that screen again. All right. So we get a number like that. It's gigantic, and that's the issue. Negative exponents. In other words, 2 to the, and here I think I have to put that in, 2 to the minus 64 are a possibility. No, let's not do that. Let's do 2 to the minus 3. Go back to our first one here. Then this becomes actually the fraction 1/2. What we do is we convert the 2. When we have a negative exponent, we convert the 2 to a fraction, what we call invert it, which means, remember we said that any number can be expressed as itself over a 1. If we invert that, we get 1/2, okay, times 1/2 times 1/2, okay? And when that happens, we have to employ the principle of multiplying fractions, okay? When we multiply fractions together, we multiply the top number of the first one times the top number of the second, and the bottom of the first times the bottom of the second. And in this particular case, we're going to multiply 1 times 1 times 1. And then 2 times 2 times 2. So the answer here is 1/8, right? So a negative exponent merely is, and is a positive, is multiplying the fraction, the inverse of the base. And this can be done for anything. And it's harder to do on our silly little calculators, I think. But negative exponents can be done as well. So we can have positive and negative exponents, and we'll see some problems like that. Is everybody still with me? Please
Yes and no. I think I understand it, but I think I'll understand it better once I apply it.
Yep.
Yeah, that's how I feel.
Yeah.
I'm with Jen on that.
Okay. So we have exponents. Okay. And then let's look at groupings, and then we'll go from there into the whole concept of PEMDAS. Okay. Groupings are sets of terms in parentheses, braces, or brackets. And the purpose here is, let me give you an example of what I mean in that. So we can have a term A, let's just A plus B. That's a grouping. A, let's see, let's put that in. A plus 3 is another grouping. And here I'm going to include 2 to the second minus 1. That's another grouping. These things are processed separately. And we'll get to that when I get to the order of operations, which will be the next topic we really cover after we take another break. We can also have groupings of groupings. And what we do is we keep going out. We can either have multiple sets of parens, or we can group them in brackets. We can have A plus B plus C plus 3.
That's one grouping.
Okay. We can group groups, okay, together.
Oh, okay. I see how that.
And we can keep on doing that. We often will see multiple sets of parentheses, and the trick there is to recognize where one set ends and the next one begins. In this particular case, we've got this grouping here, which which includes two sets, two little groups of parenthetical operations first. Okay. So another thing that can happen is you can have these things, you can have parentheses within parentheses. I'm going to give you another example of that. Okay. So we have two groupings. If just like we were looking at the cardinality stuff in terms of sets, we have two separate pieces inside this set of parentheses. We've got the outer parentheses, we have the inner parentheses. B plus 8 is taken care of, has to be solved before we can add A to it. Okay. So we want to keep that in mind. All right. So is this, any other questions?
So you want to do is there a reason why you want to do the B plus 8 first? Is that how you're going to get the A? Or is that how you're going to get the answer?
Yeah, we'll get, I'm showing you that these can be grouped. When we talk about order of operations, I'll make that very clear, but that's a very good question, Harley.
Yeah, the first parentheses or the grouping in another group, you have to do that first before you can do what's between them.
Yeah, in our order of operations, we work from the innermost out.
Okay.
Okay, so yeah, there is a very good reason for that.
Okay.
And when you see some order of operations problems, which may be part of our in-class activity on Wednesday, just looking at some of those problems, some of them can get very interestingly complex. And by the way, when we actually do the in-class activity, I want everyone working together on them, helping each other. Part of the reason is because you should never actually be working completely alone, no matter where you are. I mean, admittedly, these days, a lot of us are working alone. We're at home. But hopefully, one of these days, we'll get out of this and be able to get back into working in a group setting again. But nonetheless, we do work together. Also, I find that sometimes my explanations don't work for some people, but if you can work together, just like Anna just offered that explanation, working together as a peer group, I find can often teach you other things than I can. So I want you to work together.
Okay.
As I said, part of my problem is mathematics to me is second nature. And I know that nerds like me are just, that's our problem.
I can understand that.
I like it.
So, we do have to work together on this. Okay,
It
so
helps us stay on task.
right. So what I will do is actually post this as part of a page in the shell for you to take a look at. You can call it up and pull it down if you want. And I may I'm going to think about this. There's not There's a couple of other symbols, and I'm going to talk about relationships between numbers. And I'm going to start with the less than symbol. Less than, that means less than. Less than what? Whatever comes after it. So as an example, we might have A is less than 6. Okay. In the absence of any other information, it can be anything from 5 down to negative infinity. Right? In the absence of any other information. What we'll see, inequalities are something that we often have to deal with. So we'll talk about how inequalities work. So the less than symbol is used often, and we do have inequality equations, which is kind of an odd term because equation equals equal. Inequalities are the opposite. They're not equal. So less than symbol.
I didn't understand any of that you just said.
Okay. All right.
Can you explain that maybe?
Can I give it a crack at it?
Sure. Go right ahead.
So A is less than 6, which means that it can be 5 to any negative number.
Okay.
So it
Okay.
means that it can be less than, but not greater than.
Okay, that makes sense.
That makes
Okay.
sense.
So
Good.
A would be a lesser number than the 6 because of
Yep.
the symbol. Okay, got you. That's perfect. Thank you.
And Jennifer and Angela, does that make sense to you as well?
Yes.
Good. We also have greater than. Anytime you see something like less than, whoa. Funny.
Arrow.
Yeah, that must be a keyboard thing. Aha. I know how to fix that. There we go. So if we have A greater than 6, that means anything from 7 all the way out to infinity. We also can use this notation to set a value in between. Boy, my fingers are not working today.
Happens to the best of us.
Right. Yeah, okay. So we can have, say, -5 is less than A, which is greater than 6. Okay, or rather, the reverse operation, excuse me. We want that -5 is
Okay.
Greater than?
And A is less than 6. This means that 5 -5, and that means A is between -5 and 6. In other words, -4 to 5. That's a range.
-4 to 5.
-4 to 5, yeah.
The +5, right?
Okay. +5, right.
5, yeah. Okay.
Note here, the 6 doesn't have a sign in front of it, so it is assumed to be positive.
Positive.
Okay. So we can have a value in between as well. So, and we can also have this as symbols, but we want to look at these values as these symbols that we use. So we have and then we want to have some rules sign-based rules for multiplication and division. So I want to write that in now. Okay, so first off, positive times positive numbers result in a positive answer. So 3 times 5 equals 15. I'll put a few more here. So positive times positive is a positive.
Positive times a negative is a negative.
That's right. A positive times a negative is equal to a negative. In other words, 3 times minus 5.
Did you mean to put equal at the beginning or plus?
No, I didn't. That was supposed to be positive. The problem is my keyboard. This was different than on some other things here. So it equals a negative. Great. So 3 times minus 5 equals minus 15, right? Now, a negative times a negative
equals a positive.
Equals a positive. This is,
That I know.
yep, got minus 3 times minus 5, again, equals 15. Okay.
It's kind of like a negative ion plus or times another negative ion equals a positive ion.
Exactly.
That's the only thing that I took with me from high school is 2 negatives can make a positive.
Yeah. You know the joke?
What's the joke?
The joke is that in an English literature class, professor says, well, a negative times a negative is a positive when you're writing a sentence. So you can't have, if it's not, that means it is, right? But
Right.
there's no such thing as a positive times a positive being a negative. And then somebody reaches out from the back of the room and says, yeah, right. So, that's another nerd joke.
I like it.
So anyway, the same with division, okay? A positive divided by a positive is a positive. A positive divided by a negative is a negative. A negative divided by a positive is a negative. And then a negative divided by a negative is a positive, okay? So we have those rules. So when we have those combinations, we have to remember that. That's an important thing to remember when you're doing when you're solving equations, which is why another reason we have the order of operations. So it's time for a second break.
Okay.
So let's do that. And then I'll talk about order of operations, known as PEMDAS.
Okay.
Sounds good.
Okay. So
I took more of my fair share of algebra classes, so.
Okay, everybody ready to start again?
Yep.
Okay, let's start talking about order of operations. And the acronym PEMDAS, P-E-M-D-A-S, is used. It's something to remember. It's kind of a silly acronym. Please excuse my dear Aunt Sally. It tells us exactly how and in what order to solve any algebraic equation. So the P stands for parentheses, the E for exponents, the M for multiplication, the D for division, the A for addition, and the S for subtraction. Now, multiplication and division are often combined. You can do either one in any order. You have to look and see what makes sense for each equation. Same for addition and subtraction. But the critical things are to work with parentheses, exponents, multiplication, and division. Let's see, let me pull something out here.
Sorry, I had to help my mom with the new umbrella.
Ah,
Taking a little longer than expected.
not a problem. So let's take a look at and see if this works. See if I've been able to copy this. No. Yeah, here we go. I may have to fix this. Copied it off of a PDF. Okay. That didn't work. Okay. Okay, so here is an algebraic expression. Okay, here's an algebraic expression. And I think we'll change that to a division sign. Okay, so the order of operations says we do the work in the parentheses first. Okay. Now here's an example where we're multiplying, the parenthesis contains an 8 plus 4 divided by 10. Here is where we make the decision that the division has to go first, because what we're doing is adding 4 over 10 to 8. So we can view this as being actually in its own parentheses. Okay. So here we're going to simplify this to, and I'm going to just copy this. Doesn't like that. Okay. So we're going to make this 2 to the third times 8 plus, and 4 over 10. If we divide 4 by 10, we get 0.4. You can do that on your calculator. Use calculators when needed here. I don't have a problem with using calculators. You'll have them all of your life. You have them on your phone, you have them on your computer, you have them on your desk. So make use of them. Just, you still have to know what you're doing. All this does is keep you from making silly arithmetic mistakes, which everyone, including me, makes. Okay? So now we have prepared this. We do, so now we clear this parenthesis by adding 8 and 0.4. So now we have come down to 2 to the third times 8.4. So the next thing is we go back and look at our order. We've cleared the parenthesis. Now we take care of the exponents. Remember, 2 to the third is 2 times 2 times 2. So this
Which is 8.
8, right? Thank you. Times 8.4. So we get our answer, and that's going to be 67.2. If I have done my mental arithmetic correctly, check everything I do, because I do a lot of math in my head, and I have been, it's not uncommon for me to make errors.
You're right.
Okay. Okay. Now, so that's one example. Let's pick another. I will pull up another example here. And I'm just going to write that one out. Do another example here. Okay. 2 times paren 3 to the third minus 5 plus 8 paren. So how are you going to solve that?
Exponent first.
Okay. And what's 3 to the third?
27.
Okay, 27 minus 5 plus 8. All right, what's next?
The addition?
We can do the addition or the subtraction. This is a case where it doesn't matter, but that's a good. The addition's fine. So what do we get?
My brain has froze.
2 times parenthesis 27 subtract 13 parentheses.
Now, serial subtraction and addition, okay? So we are taking 27, we're subtracting 5, and then to that result, we can add 8, or adding 8 and subtracting 5, either one. Does that work? Does that make sense?
Yeah, so you either subtract 5 or you add 8.
Right.
Okay.
That would be your first step.
And then you times it by the 2?
Well, you have to do both.
Yeah.
You have to both subtract 5 and add 8, right?
Right.
Unless it's a
Yeah.
different type of one where you have to put the outside in, but that's
So if we're going to subtract,
way further.
so if we're going to subtract first, we'd subtract 5 from the 27, right?
Mm-hmm.
It would make it the 23. It'd make it 2 times parentheses 23 or 23
22.
or 22. Sorry. Yep. My math is off.
That's all right. That's why I suggest using calculators.
And then it's 2 times 30. And you get 60.
Or 60, right. So we have cleared the parenthesis. So we did everything there. The order of operations says we do the exponent first, which is what we did. And then again, it doesn't matter if we subtract 5. I generally say to make things consistent, we should work from left to right when we have a set of multiplications, divisions, and additions and subtractions. The order, generally speaking, the order of addition and subtraction isn't going to matter. So if we had added 8 to 27, we'd have gotten 35, and then subtracted 5, we'd have gotten the same 30.
Okay.
But generally speaking, when we have a sequence of these actions, we will work from left to right. But again, it's understanding that we have various terms, right?
Mm-hmm.
All right, so I'm going to pull up, see if this is going to work. No, it isn't. All right. Let's see if I can do another share.
So there's several different parts of the share button. Did you hit share my screen or just share Word doc?
Well, it's not a Word doc, it's PDF, and I'm trying to find it. And it should have, here we are. Here, that's what I wanted. Okay. So let's take a look at this one here. And you guys go ahead and solve it.
Well, 8 plus 4 is 12, but it's 2. It's 8. Got it.
I think I need to walk through it again. My brain's fried.
That's okay. Let's take a look. The first thing we have to do is clear the parentheses.
Right.
So we have 2 sets of parentheses. It doesn't matter which one you clear first. So let's start with the easy one, 6 minus 4.
2.
That's 2. Now in the second parenthesis, we have a multiplication and an exponent. So the PEMDAS rules say first do the exponent. So what is 2 squared? 2 times 2.
8. No,
Wait. 2
4.
times 2 is 4.
That's 4, right. Yeah, we've been using 2 times 3 too much, yeah.
Yeah.
So that's 4. So now we have 3 times 4. So what's 3 times 4?
12.
Right, now we have 12 divided by 2.
Which is 6.
6, and that's the answer.
Can you show me that written out by chance? Because I learn better that way, just to see it.
Sure, I will. I'll put that into the Word document that we had.
Okay, thank you.
All right. Okay, everybody see that one?
Mhm.
Okay, so I'll write it out. And I'm going to use the slash symbol instead of the division symbol because that's easier to get to. Is that okay?
Yeah.
Mhm.
Whoops. No, 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 no. You're not supposed to do that. Okay. So the first thing we did was clear the 6 minus 4. So we've got the same. We've got the same here. So this is divided now by 2. So now we have to work with this one. And this becomes
3
okay,
times
and
4.
2 squared is 4.
You're off the
What's
parentheses.
going on with this?
I think you might need to either
Yeah, I'm
have,
just thing with this keyboard. It's funny. It's an add-on to my computer. Okay,
it might not be calibrated correctly.
it probably isn't. So now we've gotten it down to, the next step of clearing the parenthesis is to multiply 3 times 4. And now we have 12 divided by 2.
Which is 6, right?
6, yes. So we've done this stepwise. We cleared one set of parentheses. It didn't matter which one we did first. When it just says parentheses, but we have to clear all parentheses before we can do anything else. So then but then the inside of the parenthesis is subject to PEMDAS rules. So the first thing is the exponent, and then the multiplication is a second step. That makes sense, Haley? Harlan?
Following my dear Aunt Sally, right? It's the multiplication, division, or addition, division, and subtraction.
Yep, we follow that when we're working inside the parentheses. We use the PEMDAS rules first, the order of operations within the parenthesis to clear it out. Once the parentheses are gone, then we finish the rest of the process.
Okay, that makes sense.
Okay.
It's easier seeing it written out like that is way easier on my brain.
Okay, not a problem. Not a problem. Let's see. I can bring up that again. All right. Let's take a look at this one. 2 to the 3rd plus 8 minus 4 divided by 3. Go ahead and work on that.
I'm just going to put a thumbs up for when I have it.
Sorry, Anna?
I'm just putting thumbs up when I got it.
Ah, good, good. Yeah.
So I don't ruin it for everybody else.
That's okay.
I hope I did this right, but I don't know.
What did you get?
3.33.
Okay. We'll go through it.
Okay.
I got 4, but I feel like I'm a little off on that.
I got that too, so.
Okay. Well, good. I feel a little bit more confident about my answer then.
So let's go back to this and we'll write it out, okay?
Oh, maybe did I write it different? Oh, I think I wrote it backwards. That's, I went dyslexic. My brain is fried.
That's okay, it happens.
Put my glasses on. Oh, shoot. I totally went backwards.
I find that I have to be kind of careful with numbers because when I was a little kid, it happened all the time. With numbers, I flip them a lot if I try to go by memory. And so I just have to make sure that I write it down and then it solidifies in my head.
That's
Whatever
probably
way works is the proper way for you to do it, whatever works for you. So to solve this, we have a parenthetical and a division, right?
I did write, did we all, I think it was 2 to the 3rd, wasn't it on
Yeah,
that?
it was 2 to the 3rd.
2 to the 3rd.
So am I right? I don't know.
You did have it right, Harley, but I think, Mike, I think you
Flipped them.
just flipped those
Did I
two.
put those 2 to the 3rd? Yeah.
I'm dyslexic.
Nope.
It's normal for me.
Okay, you're right. I flipped it. Yep.
He's just making sure we're on top of our games here.
Yeah, right.
It's like
We're
that
all awake.
Backwards or
5
something.
would not equal 12 if it's.
Yeah, I was
reading
like,
that
hold on, that's not the same thing. Like, maybe I got it wrong.
All right. So 2 to the 3rd.
Okay.
So the first thing we do is clear the exponent, right?
Okay.
So this becomes 8
plus 8 plus
plus 8
minus 4.
minus 4 divided by 3. Okay.
Need a plus
So it should
sign.
be a plus.
Yeah.
Hit the wrong thing.
It's like
Plus. Okay. So that's 8 plus 8 is 16, right? And we keep the parenthesis in place until we get it, all the operations done so that we don't make an error. Okay. So this becomes now 12
whoa.
divided by 3, which is 4.
Okay, I was a little
Well, I
off.
did it right.
My math was a little off. Yep, you did it right.
Yep. Again, calculators and checking.
Calculator it is.
Yep. Calculators are good. There's really no reason not to use them. I mean, you have to understand the order of operations. You can't, most calculators, you can't just plug in an equation and say, okay, solve it.
Right.
Yeah, I have a few family members that are human calculators, so I've picked up a few things throughout the
You're
years.
lucky.
We're just doing it in my head, and I'm like, okay, got it. Just kind of going to what I'm doing.
Excellent. Okay. So does all of this make sense, this order of operations?
Yes.
Yep,
We will
so
be
far.
doing more of these, probably. I'll get some stuff together for our in-class activity on Wednesday, and put together some hopefully more complicated things to work on together to really hone your skills at this. But again, with math, it's always a good idea to check. And where possible, do things in a different order. Now down here, we had this problem, which was 2 to the third times 8, or rather 2 times 3 to the third minus 5 plus 8. So sometimes it's best to do the 3 to the third, but then reverse the order of the addition and subtraction and check your results. That way you're not honing in on repeating the same error.
Okay.
And you should check when you're working with numbers. You need to be willing to go back and check them rather than just assume you're right. Anything that's important. Let's just say you're doing a profit and loss estimate for your company. You should always be making sure that, first off, you haven't transposed numbers. That's one of our favorite tricks. Everybody. You want to be sure you haven't done that. You want to go back and check, and if at all possible, find a way to do the calculation in a different order. But you have to stay within the PEMDAS rules. Okay. So when you're looking at these things, you should go back and check, because what you don't want is to take a mistake up to your boss.
Mm-hmm.
Right? That can result in real problems. If not for you, then maybe for your company. So you want to be careful about that. I used to do sales forecasting in the pharmaceutical industry for a while. And first off, it's a pretty squishy subject because it all depends on assumptions. But I would go through and make sure every time that that I produced a number, that it was clear how it was produced and it was mathematically consistent and correct. And so we have to do a lot of checking on these things. But, and when you're doing your, I want you to check this when you're working on your assessments, you don't have a time limit. So take your time and check everything that you do and be sure you understand what you're doing. And remember, if you have a problem, if a question makes no sense on your assessment, please contact me. I check my emails regularly, and email's the best way these days to contact me. Ask. If there's a problem, ask. And I'll get back to you as soon as I can. I can't promise instantaneously, but especially with cleaning up this mess that we're dealing with in the house, but I will get back to you. Okay. So, any other questions? Okay, let's spend the rest. We've got about a half an hour left. So let's spend the rest of that time working on your discussion for this week. And you may want to look at the assignment and see if any of it doesn't make sense. Some of it's going to be PEMDAS and some of it's going to be material we'll cover on Wednesday. But take a look at that and let's spend the next half hour getting started on getting those things going. Okay.
Do you do you appreciate the like YouTube videos in your discussions?
Yeah, that's fine.
Okay, awesome. Just quick
Fine.
question.
Yeah,
Awesome.
I don't have a problem with that at all. In fact, I like to see the creativity that comes in with
Okay.
that.
Okay.
I find that a lot of times I can learn from you guys.
Okay.
I'm going to take my video off so you guys don't see my thinking face when I am working. A little scary.
Go right ahead.
I'm gonna exit out of here.
Okay.
I will see you Wednesday, yes?
I hope so.
Um,
I'll be here.
that meeting is at 6, right, tonight?
6 tonight,
Yes.
yes. So it's the first roughly half hour of the nighttime class time. So
Okay, and is there a Zoom number on that?
on the announcement, there is a Zoom address. Yeah. And it's
Okay,
also in the Canvas announcements.
awesome. Thank you very much.
You're welcome, Harley. We'll
Let's
see
get
you
to work.
Wednesday.
All right, thank you.
Charlie,
Bye, guys. You have a good day.
you too. Bye.
Bye.
I can't spell veterinarian. Woohoo!
I usually blame the keyboard for that.
No, I blame myself because I didn't know how to spell it.
Okay, for those of you who are there, I'm going to add something to the end of this recording that's not meant for you, but for those who were not here for whatever reason and have to watch the recording. So for those of you watching this recording, you need to send me an email, and my email can be found in the instructor bio information in Canvas. You need to send me an email with the word Swansea, SWANSEA, in the body in the email to let me know that you've listened to this.
So I'm doing 3 different ones on there for the discussion.
That's not a problem. So where do you actually work?
Right now, I'm working at Ross. However, with my career that I'm going into is computer science and technology.
Okay.
So I have Terry as my instructor most of the time.
Oh, great. That's a great field. Well, you'll need math.
Yes, especially for the coding and the programming.
Yeah.
Programming is huge with algebra. Get one thing wrong and the whole thing goes.
Yeah, and writing, just writing. Many years ago, I wrote data analysis computer programs for a mainframe computer. And yeah, you make one little error and the whole thing is completely botched.
Yep. It's not, what I've heard is it's not fun to try and correct that.
No.
Then you have to go through all of it.
Yep. You find one little error in one little line of code. And it's a mess. When I first was doing computer programming, we didn't have batch processing, and we had to do punch cards, and that was horrible. Finding the errors.
Sounds like it, because that would, I don't really know what to say to that.
There's not much you can. Fortunately, we don't have to do that anymore.
Unfortunately, we don't have to listen to the dial-up tone anymore.
Yeah, no kidding. That's another one. But things have changed a lot. So, I no longer do any programming because it's just I'm so far out of that realm these days. But it was fun while it lasted. I enjoyed it. But then I got off into actually getting my hands wet in the chemistry lab, so I lost interest in the programming side.
Yeah, that would do it.
Yep.
I would have gotten an A in my chemistry class for my junior year if I took the final.
Oh.
I didn't take the final, so I got a C instead.
Oh my. Why didn't you take the final?
That was the year that I started to ditch classes.
Ah. Yep.
Yeah. Because I was getting picked on for being too smart.
Yeah.
Yeah.
That can be a problem.
Yes.
So, yeah, it always bothers me that people get picked on for being good students. It's sort of like you're supposed to be stupid.
Yeah, I've learned to play the blonde card a lot with my friends because they don't understand what I say occasionally.
Right.
And they have to go back and I'm like, okay, this is what I'm saying. They're like, oh, say it in normal people tongue.
Yeah.
I am.
Right, I am. I'm the normal person here. Yeah, I had a boss one time who he had his PhD from MIT, so, and his wife had her master's degree. So their kids were not, their kids were very smart, but his older son got involved with a crowd that thought it was real cool to be stupid. And then at the end of the year, he found out that one of the leaders of the group was getting straight A's and never, encouraged people to be dumb instead of getting their straight A's. So he felt betrayed. So it's a really silly thing to do.
Oh, yeah. It's very simple to fall off the wagon for being smart.
Yeah.
Which is probably why all of the great people like Nikola Tesla and Albert Einstein had problems.
Yeah. Yeah. When you're smarter than everybody else around you, it does cause problems. So.
I was around a lot of people who dropped out of high school, so.
Because they were smart?
No, because they didn't care where the future took them.
No, that's too bad. Yeah, we've had, I've had students that dropped out of high school and took their GED because, high school just wasn't teaching them anything. So,
Yeah, I was planning on doing that. That's why I know Laura. However, I went back to high school and I mainly just kind of messed around besides being pregnant with my son, but messed around as in not really do much work because I had finished it before it was due.
yeah.
So I was kind of sitting in the classroom and my teacher was like, why don't you just do the rest of the work for this semester and then you don't have to come back until next semester. I was like, okay, got it all done, went home, slept until I gave birth to my kid.
Well,
And then
how old's your child?
he's 2. He'll be 3 in October.
Uh,
So it's definitely entertaining to see him grow, but I also know that I need all of this.
yeah, you need to keep him occupied, keep him using his brain, because as we like to say, the apple doesn't fall very far from the tree, so he's probably pretty smart.
Yeah, which means that I have to teach him different ways of doing it in a creative way when he's younger, because that's how I would learn. But now I'm more factual for getting things done. My brain switched sides.
Ah,
Yeah,
yep.
so it's always fun.
It is. It is.
I'm trying to see what part of this little paragraph I want to use. This is fun.
Can I help take the box?
Oh boy, my son's annoying my mom.
What was that, Anna?
My son is annoying my mom.
Oh,
All I hear is little squeaks
oh, I
here
hear.
and there. Oh yeah, not the first time. Oh boy, he was in the trash. That's.
Okay, so we have,
3 minutes.
we have 3 minutes left. So do you have any other questions or anything?
I
Not
don't
that-
so far.
Okay.
Oh, you're muted still, Jen.
Thank you.
You're welcome. I'm like, wait, is she talking?
I don't have any questions now. I kind of feel like once I get into the assignment, I'll have some questions, but I think I'll wait until after Wednesday to get started on the assignment.
Okay. Yeah, just remember you can contact me or Laura if you need help.
Okay.
You know my number. I don't know how much help I'll be, but let me know if you want to study together or something.
Sounds good. I think that would be a really good idea, just to kind of work as a team on some things.
that would be perfectly fine.
Yep.
Work together, help each other. You know, the workplace should be a cooperative place to be. So you should get used to collaborating on getting things done.
Sounds good.
Yep. And anybody else's perspective on problems is helpful too.
Very true.
That is true. If you guys need any help, hopefully when we get back into class, I can give my number out to both of you, so
Okay.
you can text me to see if I can help you or not. But
Alrighty. Thank you. That sounds good.
You
you're welcome. All right, I'm gonna
guys
go.
later. Yeah, go take care of your baby. Your mom
Bye.
go nuts.
Go rescue your
Yeah.
mother.
All right, bye guys.
Bye.
See you guys Wednesday.
Yep. Have a good Tuesday and see you Wednesday.
Yep. See you guys.
All right. Bye.